Okay, so everyone, I bet you are as excited as me because we get to learn about what the Ackermann function is. Let's actually see what it is. It's named out of Wilhelm Ackermann. Okay, it's a function. You know what? Ask Morten what this function does. He works with computers. I work with machine learning. I don't know, but I look at it and I think this one looks cool. So let's just try to implement it and see how we would implement it, because I think that's a little bit easier than actually understanding what it's supposed to be. So it's a function a that takes two integers as input. I guess these are integers. Yeah, it looks to be integers from the actually we are told they're integers. They take two integers as an input, and then if the first one is 0, we should return the second one plus 1. And in the other cases we should do different things. Again, I'm going to just use my usual trick and just focus on the simpler case first and then try to expand on that. So we have a little bit of an example here. I'm just going to copy paste it, and this is supposed to be 125. So I go back and I find Ackermann. Go Ackermann. So let's say we do a print of Ackermann, and this is supposed to be, no, go away. Why are you doing this? This is so annoying. It's supposed to be 100 and, was it 55 or was it 25? It's 125. Okay, so this is a little too excessive. Actually, no, and then what I wanted to do was that I wanted to focus on the simpler case first, where m is equal to 0. So let's do that. So the first one is m and the second one is n. So this is supposed to be what? It's supposed to be n plus 1, so it's supposed to be, I guess, 5. So we print out 5 like this. So these two, so now we printed out that this should be 5. Let's see what happens if I run it. What happens is that I just get an error here. But I think, armed with all we know, we can easily begin to address this. So if m is equal to 0, I would test that like this. I should return n plus 1. Like this. And now it should work. So it works. And if I change this to a 7, it should probably be 8. And it works. Great. Now you can probably imagine what the next thing I do. I go down to this case. If m is greater than 0 and n is equal to 0, I should return this thing here. So let's see what happens if I just say m is greater than 0 and n is equal to 0. Then I return Ackermann function of m minus 1 and 1. Like this. I mean, God knows why is it defined like that. It would be really interesting to know, but I don't know. Now let's think a little bit about what's going to happen here. Because what's going to happen here is actually something that's a little bit bad. Because when I call the function, so let's say I do print, and let's do a case that matches this. So let's say m is equal to 3, and let's say that n is equal to 0. What should happen here? Well, what's going to happen is that m is equal to 3, so this condition will not be met, but this condition will maybe be met, and this one is 0, so it will be met, and then it's going to call Ackermann. And the input arguments that is going to give to Ackermann will be m minus 1, so that would be 3 minus 1, so actually it would be 2, and then 1. But what happens next? I call my function again with these input arguments. So m will be equal to greater than 0, that would not be true here, it would be true here. N would be equal to 1, so that would not be true. So it would actually fall through, and what will happen is that we hit this exception. Not in the first go of the Ackermann function, but in the second go. Let's test that's the case. So it gives us an error. So our little strategy of doing this incrementally is not completely going to work here. And I can see that because I try to reason about what my program does, which is always a good idea. So we need to properly implement both branches, all branches of this fork equation in order to make this work. So let's look at the last one. This is if m is greater than 0 and n is greater than 0. So let's look at that. If m is greater than 0 and n is greater than 0, what do we do in that case? Well, we still need to use the Ackermann function. So we compute the Ackermann function, and what do we give it as input arguments? We give it m minus 1, like this. And then we give it the Ackermann function evaluated at m and n minus 1. It's completely unclear to me why this program will actually terminate at this point. But maybe we can reason about what happens in this example here, because we call it with Ackermann of 2 and 1. So what happens in that case? Well, what happens in that case is that I call the Ackermann function again, so m is equal to 2 and n is equal to 1. This is not true, this is not true, this is true. So in that case we will evaluate this branch here. So we're going to evaluate it with m and n minus 1. So that would be m equal to 0. So it's going to actually return this quantity down here. Like, let's think about what it's going to do. It's going to return Ackermann of m minus 1 of this thing here, which is going to be Ackermann of 2 and 0. Ackermann of 2 and 0 is going to be no, it's going to be actually this branch, because m is greater than 2 and n is equal to 0. So that would be actually Ackermann of... it's really complicated. It's going to be Ackermann of... Oh god, this is complicated. Ackermann of 1 and 1. And what happens then? Because now we're evaluating Ackermann of 1 and 1. It's not this, it's not this, it's this one. But now n will be equal to 0. Oh, yikes. I see why this is complicated. It's actually too complicated for me to reason about what it does, even in this simple example that I have here. So let's actually just see if it works. Like, I mean, we are told what it's supposed to be. Let's see if it actually works. It works. I think this, not a primitive recursion. I think what this means is that it's hard to reason about what it does recursively. I guess that is what this means. Total computable, God knows what that means. Basically, all of this stuff amounts to this is a really, really complicated function to think about, the way that I tried to do here. But it's also simple to define, so that's why computer scientists love it. Apparently the Ackermann function just does what the Ackermann function do. I'm really excited about this. Let's check that this works. Ackermann of 2 and 5. Let's see. Let's print it out. So this was supposed to be 13, right? This was supposed to be 13. Let's see if we did it right. Yeah, apparently. But I mean, try to reason about what this does up here. I mean, I'm really not sure. Actually, let's just do a little experiment for science. Let's print out everything that it does along the way. So now we're just going to print out m and n and see how many times the Ackermann function is going to be called in order to compute 13. So this is apparently all the function calls we get to the Ackermann function. Yeah, that's actually pretty cool. Let's see. Maybe my computer will just stop now. Yeah. Yeah, that was Python. That this is called blowing the stack. It basically means that you call the function recursively too many times. Python doesn't like that. Okay, this is a complicated function. Very interesting. Let's check if we did the test correctly and just leave it at that. I think I oversold how much I could reason about recursion. I really thought I could just do a really cool example and seem very clever, and that was not the case. Apparently we implemented it correctly, at least according to these tests, but I have a feeling these tests are not super exhaustive of this function. Why are there 2 tests for Ackermann? Looks like somebody copy-pasted a little bit of code too many times. Both of them worked, and there's also a little bit of a copy. Interesting. And also here, somebody has been working on these tests, I guess. Okay, so now we're done, and now we get to the project work. And I think I'll stop this video here with this little excursion into Ackermann land.